We are living in the midst of a telecommunications revolution. The means by which people can exchange information with each other across vast distances are expanding in number, scope, and sophistication so rapidly that we can scarcely keep track of them, much less understand how they all work. Today, we'll begin a 4-lecture introduction to telecommunications technology. I can't adequately cover the full scope of this subject in just a few lectures, and so I'll be focusing on just 3 representative technologies that are quite likely to be part of your everyday life: the traditional landline telephone, the cell phone, and satellite communications. Along the way, I'll also talk just a bit about the internet, primarily because today, telecommunications and the internet have become so intertwined that we really can't discuss one without the other. But as I noted back in our very first lecture, a detailed treatment of computers and the internet is beyond the scope of this course and my own expertise, so we won't be venturing too far down this path. So let's begin with a few big ideas about telecommunications. In general terms, any modern telecommunications system works by encoding information in a carrier signal and then sending it from one location to another through a communications channel. The carrier can be an electrical current, a light beam, or an electromagnetic wave. The encoding can be analog, meaning that the signal is continuously varying, or digital, meaning that it's made up of a series of on-off pulses representing ones and zeros. The channel is the pathway through which the stream of information is sent. If the pathway is a physical medium like copper wire, coaxial cable, or a fiber optic line, then we call it a circuit, though it's important to recognize that one circuit can carry multiple channels. If the medium of transmission is wireless, as would be the case with radio, microwave, or infrared communications, then the channel is defined as a logical path rather than a physical one. We'll explore this latter concept more fully when we discuss multiplexing in the next lecture. For now, we'll examine the low-tech end of the telecommunications spectrum, your local landline telephone system, which uses analog encoding of an electrical carrier signal that's transmitted on a single-channel circuit of copper wire. Today, in a telecommunications environment dominated by technologies far more sophisticated than this one, the landline phone system is widely known by its very creative acronym POTS, or Plain Old Telephone Service. I swear I'm not making this up. And while I believe very strongly in using correct technical nomenclature when I teach, I shall refrain from calling this system the POTS for obvious reasons. Plain Old Telephone Service is indeed very old. The telephone itself was patented by Alexander Graham Bell in 1876, and by the late 19th century, a reasonably well-developed telephone network was operating in the US. Apart from rotary dialing, which was introduced in the 1930s, and touch-tone dialing in 1963, this local end of the system has changed remarkably little since then. Conversely, virtually every aspect of our telecommunications system above the local level has changed radically in just the past 20 years. To establish some context, let's look at a highly simplified depiction of the Public Switched Telephone Network, or PSTN, the telecommunications system within which the plain old telephone service resides. At the lowest level of this network are individual subscribers and groups of subscribers, the latter corresponding to residences in an apartment building or offices in a commercial establishment. These groups are connected to a private branch exchange, or PBX, a switching system that allows both internal communication between any two subscribers within the group and external communication between any subscriber and the outside world. For both individual subscribers and PBXs, The gateway to the outside world is a higher level switching system called the local exchange, housed within a facility called the central office. Note that each individual subscriber is directly connected to the local exchange by a subscriber line, also called a local loop, while the PBX is connected by a local exchange trunk. Now, in telecommunications lingo, lines and trunks are basically the same thing, except that a line is designed to support the calling load associated with one person, while a trunk is designed to support multiple users. So what's the local exchange? Well, back in the day, it consisted of a platoon of human telephone operators who established phone connections between subscribers by physically plugging pairs of wires into a switchboard, like this. Today, the exchange still performs this switching function, but the process is now fully automated. In the US, every local exchange is assigned a 3-digit code, which corresponds to the 4th, 5th, and 6th digits of your 10-digit telephone number. Now, there are about 19,000 local exchanges in the US, and since 3 digits only yield 1,000 unique numbers, from 000 to 999, all of the 3-digit local exchange codes in the US can't possibly be unique. But each one is unique within its assigned area code. And that is precisely why we need area codes. Every individual line that connects to a local exchange, either directly or through a PBX, is assigned its own 4-digit code called the subscriber number. And as you've probably guessed, these are the final 4 digits in your phone number. Since all subscriber numbers assigned to a local exchange must be unique, it's clear that a local exchange can't serve any more than 10,000 subscribers. Otherwise, there wouldn't be enough phone numbers to go around. And therefore, even a modest-sized town needs more than one local exchange. And by the way, more than one exchange can be physically housed in a single central office. Now, if you're placing a call to another subscriber within the same exchange, the call is simply routed through the local exchange to the recipient. If you're calling a subscriber who's located in the same city but connected to a different exchange, the call is passed up to the next level of the network hierarchy, to a facility called a tandem exchange, sometimes called a tandem switch, and then routed back down through the relevant local exchange to the intended recipient. If you're calling someone in a different area code, the transmission will be routed through a toll center and then onward. And if the recipient is in another country, it will also pass through an international gateway. Now, with this big picture overview in mind, let's focus on the two components of the public switch telephone network with which we interact directly every day: the telephone and the subscriber line. The subscriber line is nothing more than a simple pair of thin copper wires running from your telephone directly to the local exchange. Often called the local loop, these two wires actually constitute a DC electrical circuit that closes when you lift the telephone handset from its cradle and opens when you set it back down. This circuit is powered by a large bank of batteries located at the local exchange. And that's why, when your electrical power fails, your landline phone keeps right on working. The signal passing through the local loop receives no electrical amplification. And since the strength of any electrical signal loses power or attenuates quite significantly as it's transmitted through copper wire, the local loop is typically less than 2 miles long. This means that your local exchange is literally close to home, and the local loop really is local. Now, one of the marvels of the plain old telephone system is that these two little copper wires carry so many different types of information: the dial tone, ringtone, busy signal, dialed numbers, and of course, incoming and outgoing voice signals. In recent years, we've also added call waiting, caller ID, speed dialing, conference calling, internet communications through digital subscriber line or DSL service, and maybe even data from your home security system or thermostat. All of these information streams are controlled and synchronized by your local exchange, which serves as a sort of telecommunications traffic cop, keeping everything moving in the right direction. We'll discuss these functions in more detail shortly, but first, let's turn our attention to the telephone itself. Now, a standard landline phone has the following main components. On the handset, a microphone here, which converts sound waves into variations in electric current, and a speaker here, which converts those variations in electric current back into sound. Within the telephone housing, we find a switch here, which closes the local loop when you lift the phone handset off the hook and opens it back up when you place the phone on the hook. And a ringer, which remains permanently connected to the central switching office even when the handset is on the hook. And finally, a bunch of electrical circuitry that, at first glance, might appear to be indistinguishable from magic, but is actually quite understandable. Now, we'll return to this circuitry in a moment, but since this is the first time we've seen microphones and speakers, and because these technologies are present in many other kinds of everyday devices as well, let's first spend some time looking more closely at both of these technologies. There are several different types of microphones, but the condenser microphone is the most commonly used in landline telephones. This device, located in the lower end of your phone's handset, has two main components: a very thin metal plate called a diaphragm, and a thicker plate mounted just behind it, with a small gap between the two. When these plates are connected to an electrical circuit, they function as a capacitor. Now, in general terms, a capacitor is an electrical component consisting of two metal plates separated by a non-conducting material called a dielectric. In the case of our condenser microphone, the dielectric is air. Now, recall that when a battery is connected to a normal load, like this light bulb, electrons flow through the complete circuit from the negative battery terminal to the positive terminal. But when a capacitor is connected to a battery, there's no longer a complete circuit because of the dielectric in the capacitor. As a result, current flows only briefly as electrons move from the battery's negative terminal to the nearer plate, and then an equal number of electrons move from the other plate to the battery's positive terminal. As a result of this movement, the capacitor acquires an electrical charge, negative on one plate, positive on the other. Once the voltage across the capacitor is equal to the voltage of the battery, the current stops flowing, but the capacitor remains charged. And now, if I remove the battery and connect those two wires together, the capacitor discharges. All of those excess electrons flow from the negatively charged plate through the complete circuit to the positively charged plate until the voltage is zero and the charge is neutral throughout the circuit. Now, in our microphone, once the handset is taken off hook, current flows briefly through this branch of the circuit to charge the capacitor. The diaphragm accumulates a negative charge, and the other plate a positive charge, and then the current stops. Now, when you speak into the mic, you create sound waves, which are really just alternating regions of relatively higher and lower air pressure, propagating outward from your vocal cords. When the high pressure half of a sound wave strikes the microphone, it pushes the diaphragm inward. This narrows the gap between the two plates, which increases the capacity of those plates to store charge. And that's because the electrostatic attraction between the charged plates increases as the gap between them gets smaller. Consequently, more electrons flow into the diaphragm and out of the other plate. When the low pressure half of the sound wave passes, the diaphragm is sucked outward, decreasing its capacity to store charge and causing electrons to flow in the opposite direction. When there's no sound, the diaphragm returns to its undistorted position and the movement of electrons stops. Well, as you know, any movement of electrons constitutes a current. And so, even though there's a physical discontinuity in this circuit, current still flows as a consequence of changes in electrical charge caused by movement of that diaphragm. Furthermore, this current varies quite precisely in proportion to the volume of the sounds that are moving the diaphragm. Thus, the continuously varying current generated by the microphone is an analog of your voice. And that's why we call this an analog signal. Now, when you place a phone call, this analog signal is transmitted to the recipient's phone and decoded by her speaker. To see how a speaker actually works, let's build one. Now note that I have formed some copper wire into a coil and attached it to the bottom of a styrofoam dinner plate. The ends of the coil are attached to electrical wires, which run back to the headphone jack for my CD player. And I'm going to go ahead and plug in that headphone jack at this time. Start up the CD. And at this time, I'm going to place the plate directly over this magnet mounted on the base. And the speaker speaks. So what's happening here? Well, I suspect we've done enough experiments with magnets, coils, and current to figure this out. The radio is sending an electrical current through the coil, and just like the current generated by your telephone's microphone, this current is encoded with variations in current flow representing sound waves. As this varying current passes through the coil, it generates a simultaneously varying magnetic field. In effect, the coil is an electromagnet, which interacts with the fixed magnet by either attracting or repelling it, depending on the direction of the current at any instant. As the coil is moved by the magnet, the plate moves along with it, and it reproduces the original sound waves that generated the encoded current in the first place. I love that piece. And here's how my very crude model translates to an actual speaker. The coil here is fixed to this rigid cone, which serves the same function as my styrofoam plate. Beyond a few superficial physical differences, the two devices are essentially the same, and they work in exactly the same way. Now let's put it all together using this diagram of a typical landline telephone's internal circuitry. Suppose you're going to place a phone call to a neighbor whose phone is on the same exchange as yours. Here's what happens. You lift the handset off hook. This switch closes and current flows through the local loop. The exchange detects this current, automatically attaches a digital signal processor to your line, and then sends you a dial tone to signal that it's ready for you to proceed. The purpose of the signal processor is to detect and decode the numbers you dial. In essence, it's a modern electronic version of those telephone operators of old. Now, touch-tone dialing uses a system called dual-tone multi-frequency signaling. In this system, a different audio frequency is assigned to each row and column of the standard 4x3 telephone keypad, as shown here. When you press any button, your phone generates a tone consisting of the two associated frequencies. Think of it as a musical chord composed of two different notes. At the other end of the local loop, the digital signal processor decodes the series of chords to determine which buttons you pressed. Now, having identified the phone number you're calling, the exchange now determines whether the recipient's phone is in use by checking whether current is flowing in her local loop, which can only happen if the handset is off hook. If so, and if the recipient has call waiting, the exchange sends an audible signal down her line to indicate an incoming call. If she doesn't have call waiting or doesn't respond to the call waiting notification, the exchange sends you a busy signal, and you hang up the phone, breaking the DC circuit, and thereby notifying the exchange that your phone is again available to receive calls. If the recipient's phone is on hook, the exchange rings her phone by sending an AC current down her line. And here's where things start getting really interesting. In the phone circuitry, notice that the ringer is on its own branch, located ahead of the switch, such that current can flow through this branch even when the switch is open. And on this branch is a capacitor, which has a very useful property that we haven't yet discussed. As we've seen, a capacitor doesn't allow direct current to flow across it because of the dielectric between its two plates. But it does allow alternating current to flow because that continuously varying current causes the capacitor to charge and discharge with each AC cycle. A change in charge always constitutes a current. Thus, even though this branch of the phone's circuitry has a constant DC voltage across it, the ringer can only be activated by an alternating current sent by the exchange for that purpose. When the recipient of the call picks up her handset, the switch closes and a different switch that I haven't shown on this diagram shuts off the ringer. Both local loops are now energized and connected through the exchange. As you speak, the signal created by your microphone follows this path, connecting to the primary side of your speaker coil, somewhat beyond its midpoint. This ingenious arrangement, a type of transformer called a hybrid coil, causes a small portion of the outbound signal to be fed back into your own speaker. As a result, you can hear your own voice very faintly in the earpiece as you speak, a subtle form of audio feedback that tells you that the system is working. It's worth noting that this feature is not provided in most modern cell phones, and I personally find the lack of it just a bit disconcerting. A reminder that the relentless march of technological progress does take an occasional step backward. Now, at the other end of the circuit, the signal follows this path through your recipient's phone. Within her handset, that encoded electrical current passes through the primary side of this coil, which induces an identical current in a secondary coil that's connected to the speaker. This process of passing current from one coil to another by electromagnetic induction is essentially the same phenomenon we observed in the transformer that I demonstrated in our lecture on electrical power distribution. You might be wondering why the signal doesn't follow this path through the microphone. The answer is that the path through the speaker has much lower resistance to alternating current. Or to use more precise terminology, it has lower impedance. And so nearly all of the incoming signal naturally follows the low impedance path. This rather intricate sequence of events is repeated for every local phone call implemented within the plain old telephone service. And for calls directed outside the local exchange, the process works essentially the same way, except that the local exchange must first establish a long-distance connection to the recipient's local exchange through all relevant higher-level exchanges, all based upon those first 6 digits of the recipient's 10-digit phone number. Well, clearly, there's a lot more to the plain old telephone service than meets the eye, and we haven't yet touched on the most impressive aspect of this system, that a single local exchange serves as the terminus for thousands of subscriber lines and must often manage many thousands of these transactions simultaneously. Not surprisingly, the largest cost associated with operating the plain old telephone service is the stringing, connecting, and maintaining of all those copper wires. Phone companies have used 2 interesting technologies to keep this cost manageable. The first is the multi-pair cable, a single cable that bundles together as many as 8,400 separate insulated copper wires to create 4,200 local loops. Within the cable, pairs of wires are twisted together at different pitches, meaning that they're wound together with a different number of twists per foot to minimize electromagnetic interference between the wires. Without this feature, all the wires would run perfectly parallel to each other, and the magnetic field generated by the varying current flowing through your line would induce similar currents in adjacent wires, causing your conversation to bleed over into other subscribers' phone lines. Multi-pair cables are easy to spot on your local power pole. They're mounted lower than any of the power transmission lines because they're not carrying high voltage, and they're always much thicker. Phone cables are also sometimes suspended from a steel messenger wire, which does the structural load carrying so that the weaker copper phone wires aren't placed in tension. The 2 wires constituting your home's local loop are connected into the nearest multi-pair cable at a splice case like this one. But to make this connection, the telephone lineman must be able to distinguish your specific pair of wires from the other 4,199 pairs in that one cable. How is this possible? Well, the answer is an ingenious color coding system that uses only 10 colors. Each individual wire is identified by 2 colors, a background color and a stripe, which is also sometimes called a marker. Paired wires have opposite background and marker colors. For example, the blue wire with a white marker is always paired with a white wire that has a blue marker. By dividing the 10 available colors into 2 groups of 5 contrasting colors, it's possible to create 25 unique combinations with 1 color from each group. Groups of 25 twisted pairs are then bundled together and wrapped with a 2-colored ribbon. And groups of bundles are then combined to create similarly identified super bundles. Thus, for example, a given twisted pair might be the black-orange wire in the white-brown bundle in the red-blue super bundle. Now here's what this system looks like inside a splice case. The efficiency of multi-pair cable notwithstanding, it's still inherently inefficient to run a separate local loop from each individual subscriber all the way to the local exchange. This is particularly true because a given line is typically in use for only a small portion of each day. To address this issue, many local phone systems now use a device called a remote concentrator. The principal function of the remote concentrator is multiplexing, the process of combining many signals into a reduced number of transmission circuits. Until relatively recently, concentrators merely reduced the number of twisted pairs en route from subscribers to the local exchange. For example, 100 subscriber lines might be brought into the concentrator, and recognizing that no more than 30% of these lines are likely to be in use at any moment, a trunk consisting of 30 lines might then run from the concentrator to the exchange. The switching equipment inside the concentrator merely connected each incoming call to one of the 30 outgoing lines, and each line continued to carry just one conversation. But today, the digital communications revolution has created more sophisticated forms of multiplexing that are also far more efficient. Now, that remote concentrator in your neighborhood probably converts the analog representation of your voice into digital form, and then it interweaves your voice with hundreds or even thousands of other conversations and sends it along to the local exchange on a single wire or a single optical fiber. We'll be returning to the subjects of digital communication and multiplexing often in the next 3 lectures. For now, we should note that the use of concentrators for analog to digital conversion of voice data right in our backyards is just one of many strong indicators that the plain old telephone service is really a technology on the wane. For several decades, the higher levels of the public switch telephone network have been gradually changing from analog to digital, and today the system is almost entirely digital beyond the local exchange. Many people have now foregone landline phones entirely in favor of their cell phones or Voice over Internet Protocol, or VoIP. Maybe you have too. Worldwide, digital subscribers now outnumber landline subscribers by 3 to 1. And many new homes are being connected to their exchanges with optical fiber directly rather than copper wire in anticipation of the day sometime soon when the entire system will be digital from end to end. Before that day arrives, however, we should take a moment to appreciate the plain old telephone system as a technology that changed the world and as one that still holds considerable merit from an engineering perspective. This system has many technological limitations, most notably the limited bandwidth and severe signal attenuation associated with copper wire. But the enduring advantage of the traditional analog system over its recent digital competitors is unprecedented reliability. In most places today, when you pick up your landline phone, you'll get a dial tone 99.999% of the time. And unlike your cell phone or computer, the plain old telephone service will still be there for you even when the lights go out. Next lecture, the public switch telephone network and the brave new world of digital communication. For much of this course, we've been focusing on your home and on the large-scale infrastructure systems that support it. Today we're going to shift our focus quite dramatically from the technologies that constitute your home to the technologies contained within it, from large, complex engineered systems to small, simple products and devices. In making this shift, I hope to demonstrate that basic scientific and engineering principles are just as valuable to understanding mundane gadgets as they are for understanding large, complex systems. Now, by one estimate, each of us is surrounded by approximately 20,000 everyday things, from paper clips to pencil sharpeners to clock radios. And every one of these products has something interesting to tell us about everyday engineering. Now, we won't have time to cover all 20,000 in this lecture, so how might we choose a few representative examples from which we might learn something of particular interest? Well, as an organizing construct, let's build today's lecture around the classical simple machines, a concept that actually originated with the ancient Greeks and is still quite useful for classifying and understanding mechanical devices today. Although the official number of simple machines has varied somewhat through the ages, most modern lists include these 6: the inclined plane, the screw, the wedge, the lever, the wheel and axle, and the pulley. All of these devices have the same fundamental purpose: to change the magnitude or direction of a force. Thus, to examine the simple machines rigorously, we'll turn to mechanics, the branch of science that deals with the effects of forces acting on physical bodies. In doing so, not only will we achieve a deeper appreciation for the many simple machines that are part of our everyday lives, but we'll also acquire some foundational principles of mechanics that will serve us quite well in later lectures. Let's begin with the inclined plane, or the ramp, which allows us to lift an object using less force than that object's own weight. Now, suppose we need to pull this wheeled cart up this 20-degree incline. The cart, plus the brick that's resting on top of it, weighs about 4 pounds. Now I'm going to use this spring scale to measure the amount of force required to actually pull the cart up the incline. As we can see, when I do that simple experiment, I'll pull on the spring scale, and you'll see that this 4-pound cart requires just a bit more than 1 pound to pull it up the incline. Looks like about 1.33 pounds. Why? In the science of mechanics, forces are represented as vectors. A vector is a mathematical quantity that has both magnitude and direction. For example, this force has a magnitude of 4 pounds, and it's directed at an angle of 20 degrees measured from the horizontal. For the purpose of analysis, it's often useful to resolve a vector into its perpendicular components, as shown here. These two components, horizontal and vertical, are exactly equivalent to the original force. We can calculate the magnitudes of these two components using trigonometry. For example, the vertical component is 4 times the sine of 20 degrees equals 1.4 pounds. But if your trigonometry is a little rusty, don't worry. If you simply draw the two components to scale, as I have here, you can see that the vertical component is about 1/3 as large as the original force. And that's really all we need to know for the purposes of today's discussion. Now let's return to our inclined plane. The weight of the cart, 4 pounds, is applied straight downward. In this situation, it's most useful to resolve the vector into equivalent components that are parallel and perpendicular to the incline rather than horizontal and vertical. Note that only the parallel component of the cart's weight is oriented downhill, so this is the force we must overcome to pull the cart uphill. And what's the magnitude of this component? Well, once again, it's 4 times the sine of 20 degrees equals 1.4 pounds. But again, you don't really need to do the trigonometry. You We can estimate the force's magnitude quite accurately from this scale diagram. So this vector analysis verifies what we've already observed, that we can use an inclined plane to lift a 4-pound object with only 1.4 pounds. This magnification of effort is called mechanical advantage, and this particular inclined plane has a mechanical advantage of 3-to-1. But mechanical advantage always comes at a cost. To lift that 4-pound weight with 1/3 as much force, we had to pull it through a distance 3 times greater than the height. As we shall see, all of the simple machines achieve mechanical advantage in this same way, by trading force for distance. Consider the screw, used as a fastener in innumerable products and devices, but also found in many other interesting places. Like this corkscrew. This automobile jack. And even in the rotating blades of a modern snowblower. In all cases, the purpose of the screw is to convert rotational motion into linear motion, or to convert a rotational force, which we call a moment, into linear force directed along the length of the screw. Now, a moment is defined as the tendency of a force to cause rotation. If I place my wrench onto this bolt head and then apply a 1-pound force to the handle, like this, I'm applying a moment to the bolt. Its magnitude is the force, 1 pound, times the distance from that force to the center of rotation, about 6 inches. And therefore the moment equals 6 inch-pounds, or 1/2 foot-pound. By the way, in this situation, when a moment is applied to a rotating shaft, it's also called a torque, a term we'll be using often when we discuss automotive technology a few lectures from now. So how does a screw change a moment into a linear force? Well, first, it always requires 2 matched sets of threads, one moving and one stationary. With this nut and bolt, both sets of threads are actually manufactured. There's a set of male threads on the bolt and a set of female threads on the nut. With this lag bolt, there really only is one set of threads manufactured into the device. However, the bolt itself cuts the second set of threads into the wood as I drive it inward. In either case, the bolt's angled threads translate the applied moment into a larger longitudinal force. This force drives the lag bolt into the wood, and it clamps the nut and the bolt head tightly against the connected material in the case of the nut and bolt. Now, in this sense, a screw actually works much like an inclined plane that's been formed into a cylindrical shape. And if you don't believe me, let's just wrap this inclined plane around this shaft. As we do, I think you can see where we're heading. The end result looks very much like a screw. Visualizing the threads of a screw as an inclined plane also helps us determine the mechanical advantage of the screw. If we visualize the screw as being rotated by a tangential force moving around the circumference of the shaft, like this, then the distance through which the force moves corresponds to this horizontal edge on our inclined plane. And the distance through which the screw actually moves corresponds to this vertical edge of the same inclined plane. Now, since mechanical advantage is always about trading force for distance, the theoretical magnification of force by this particular screw is exactly equal to the ratio of the large length divided by the smaller length. That is, this length divided by this one, which happens to be 2.75 for this particular screw. Most screws and bolts actually have their threads oriented on a significantly shallower angle, and so their theoretical mechanical advantage is actually much larger than 2.75. But I emphasize the word theoretical because the usable mechanical advantage of a screw is always substantially reduced by friction. All machines, simple and otherwise, are susceptible to this problem, of course. But the screw's performance is more dramatically affected by friction than most machines because the longitudinal force on the shaft clamps the surfaces of the moving and stationary threads so tightly together. A metal screw typically loses over 80% of its theoretical mechanical advantage to friction. Yet this isn't necessarily a bad thing. Thanks to friction, screws and bolts are said to be self-locking. I might be driving this lag bolt into the wood, but then when I remove my wrench from the lag bolt, it doesn't spontaneously unscrew itself, as it would if there were no friction between the threads. Now, not all simple machines are self-locking. Levers typically are not. And, for example, if I return to my inclined plane, and I pull the cart up the plane, but I remove the force, the uphill force from that wheeled cart, well, certainly it's going to roll back down the inclined plane. However, I can make this ramp self-locking by simply flipping the cart upside down. Now, friction prevents my work from being undone. As I pull the cart up the hill, anytime I remove the applied force, the cart remains stationary. But this self-locking behavior always comes at a cost. Note that now the force required to pull the cart up the hill is substantially larger. It's pretty close to 3 pounds versus the 1.4 pounds for the wheeled configuration. Thus, friction has provided self-locking for the inclined plane, but it has also reduced the ramp's mechanical advantage, just as it does with a screw. Now, onward to the third of our simple machines, the wedge. Here's a simple example called a timber wedge, and it's used for splitting wood, like this. Now, to understand how this wedge actually works, we'll be examining it in this configuration, with the device embedded in a log and subjected to the downward force of a hammer applied to the top surface of the wedge. Now let's isolate the wedge and identify all of the forces acting upon it. The hammer is applying a large downward force, which augments the weight of the wedge like this. An important principle of mechanics tells us that this can't possibly be the only force acting on the wedge. The principle of equilibrium is based on Newton's first law of motion, which says that an object at rest will remain at rest unless it's acted upon by an unbalanced force. At the moment, our wedge isn't moving, and so we can conclude that all of the forces acting on it must be in balance. Therefore, there must be other forces acting on the wedge to counterbalance that downward force applied by the hammer. And the only places where these forces can possibly occur is at these contact surfaces between the wedge and the wood. Anytime two objects are in contact with each other, forces are developed at the point of contact. They're called normal forces because they always act perpendicular or normal to the contact surface. Normal forces always occur in pairs, equal in magnitude but opposite in direction applied to the two objects. Thus, the normal forces associated with our wedge look like this, directed upward and inward on the wedge, and directed outward and downward on the wood. And by the way, this phenomenon is another manifestation of Newton's third law. For every action, there's an equal and opposite reaction. I should add that friction forces also occur along the contact surface between the wedge and the wood, but for now, we'll ignore them for the sake of simplicity. And now, by shifting our focus from the wedge to the wood, we can clearly see how this machine works. These two large normal forces generated by the wedge push the material apart and eventually cause it to split. So how large are these forces? Well, to answer this question, we return to the principle of equilibrium, which says that all forces acting on the wedge must be in balance, or more precisely, that all of the force vectors must add to zero. Now, mathematically, vectors can only be added together if they're oriented in the same direction. So before we can enforce equilibrium, we'll need to resolve these two diagonal forces into their vertical and horizontal components, like this. Now, all the vertical components must add to zero, and all the horizontal components must separately add to zero. Just like our inclined plane analysis, this problem can be solved quite accurately with trigonometry, but we can learn all we need to learn by drawing the vectors to scale and examining their magnitudes. Note that the horizontal components of the two normal forces will always counterbalance each other, while the downward force must be counterbalanced by the vertical components of the two normals. And because the angle of the wedge is acute, the normal forces must be significantly larger than the downward force. Now, my timber wedge has an angle of 10 degrees, and at that angle, each normal force is nearly 6 times larger than the total downward force. That's a 6-to-1 mechanical advantage, though the actual performance of the machine is somewhat reduced by friction between the wedge and the wood. But if you don't split your own firewood, why should you care about wedges? Well, every knife in your kitchen employs the power of the wedge. Parting this apple just as easily as my timber wedge parts wood. Each zipper on your clothing employs 3 wedges, an upper one here that splits the 2 rows of teeth apart when you pull the zipper down, and 2 lower wedges that compress the teeth back together when you pull it up. But my favorite practical application of the wedge is the one that's holding your house together, the nail. Here, the wedge is not intended to split the wood, but it does use those large normal forces to generate the friction necessary to keep the nail in place. In this sense, a nail is self-locking, just like a screw. Now, suppose I need to remove this nail. There are several different tools I might use for the job, but every one of them is a lever of some sort. This crowbar represents the simplest type. To use it as a lever, I'll place this support, called a fulcrum, as close as possible to the nail, and then I will put the crowbar in place, and when I apply a force all the way out here at the far end, the bar pivots on the fulcrum, and the shorter end lifts the nail head. Now, how does a lever achieve mechanical advantage? Once again, let's isolate the machine and show all the forces acting on it. Here's the force applied by my hand. On the opposite end, the bar is pulling upward on the nail, and thus, according to Newton's third law, the nail must be pulling downward on the bar. The principle of equilibrium says that all forces on the bar add to zero. So there must be a large upward force at the fulcrum, counterbalancing the 2 downward forces at the ends. The principle of equilibrium also tells us that all moments acting on a stationary object must add to zero. Therefore, if we designate the forces acting on the bar as F1 and F2, and these 2 distances, called lever arms, as L1 and L2, then the counterclockwise moment caused by my hand, F1 times L1, must be exactly equal to the clockwise moment caused by the load, F2 times L2. After a little algebra, this equation tells us that the lever magnifies my effort by a factor of L1 divided by L2. In other words, the ratio L1 over L2 is the mechanical advantage. The 2 lever arms of this particular 36-inch pry bar are 33 inches and 3 inches. Thus, the mechanical advantage is 33 divided by 3, or 11 to 1. In other words, for every 1 pound I apply, I get 11 pounds of force at the other end. But here, once again, is the inherent trade-off common to all simple machines. In order to gain that 11-to-1 mechanical advantage in force, I need to move my hand 11 inches out here for every 1 inch of lift in at the nail. Now, by the way, not all levers are straight bars. When I extract this nail with my claw hammer, the hammer is working as an L-shaped lever with the fulcrum here, L1 here, and L2 here. The resulting mechanical advantage is about 6-to-1. Levers are everywhere. This bottle opener is a lever. This corkscrew uses 2 levers and a screw to extract a cork from a bottle. Scissors and pliers each consist of 2 levers each, connected together at a common fulcrum. A fishing pole is a lever for extracting a fish from water. This fingernail clipper uses 3 levers to produce the mechanical advantage required to drive these 2 wedges through a fingernail. As these examples demonstrate, different types of simple machines are often combined together into a single device for enhanced effectiveness. I can think of no better example than this amazing tool, the lever axe. You know, literally since the dawn of civilization, humans have been chopping wood with axes and hatchets that look more or less like this: a simple symmetrical wedge mounted on a handle. But then about 10 years ago, a woodcutter in Finland had a better idea. Instead of relying solely on the power of the wedge to split wood, why not combine 2 simple machines, the wedge and the lever, to create a device that would split and pry simultaneously? To achieve this effect, the inventor devised this asymmetrical configuration, which offsets the axe head's center of mass from the handle. Consequently, when the blade hits its target, it penetrates and rotates simultaneously. And the rotating blade works as a lever to pry the log apart with far less effort than a conventional axe would demand. So, does it work? Well, let's head to the woodshed and give it a try. I see we have some logs ready for splitting. Let's see how this technology performs. Who would have imagined that a 200,000-year-old technology could be improved so radically through the application of just a little engineering ingenuity? Wow, that was invigorating. And now that we understand the lever, we can effectively understand the wheel and axle too. Now, in the context of simple machines, the term wheel and axle usually doesn't refer to a rolling wheel, but rather to a wheel with a fixed axle like this one. The classic device is called a windlass, which operates by converting a small force applied to the wheel to a much larger force applied to the rope that's wrapped around the axle, like this. Note that as I apply a small force to one of the handles, rotating the wheels, I get a much larger force applied to that rope, and I'm able to lift a much heavier weight than the force that I'm applying to the wheel. The analogous modern household device is the reel I use to wind up my garden hose. But many other common devices work on the same principle. These include the steering wheel in your car, knobs on appliances and faucets, and even the screwdriver, with the handle serving as the wheel and the blade as the axle. You know, when I used my wrench to drive this lag bolt into a piece of wood, I was effectively using it as a wheel and axle. And so you can see that the wheel and axle really is nothing more than a rotating lever. Now it's important to recognize that in this system, the torque applied to the wheel is exactly equal to the torque developed in the axle. But because the torque is equal to the force times the radius, the force at the axle must be larger than the force applied to the wheel by a factor of R1 divided by R2, the ratio of the wheel radius to the axle radius. And so R1 over R2 is the mechanical advantage. When I used my 6-inch wrench to turn a 1/2 inch lag bolt, I gained a mechanical advantage of 24 to 1. That's 6 inches divided by the bolt's 1/4 inch radius. Now our final simple machine is the pulley, a device that, in its simplest form, only changes the direction of a force without actually magnifying it. This single pulley allows me to lift this 2-pound weight upward by pulling downward with 2 pounds. There's no mechanical advantage here, but for a typical household example like the lifting apparatus on these mini blinds, we're more concerned with convenience than with the capacity to lift a heavy weight. In this application, lifting a heavy weight is the goal, but incorporating mechanical advantage would defeat the purpose of the machine. Now, it is possible to rig a single pulley such that it does provide mechanical advantage. Watch. In this arrangement, the pulley moves with the load rather than being fixed. And note that this 2-pound weight is now being supported by 2 legs of the lifting rope rather than just one. So the tension in each rope must be 1 pound. Therefore, the mechanical advantage must be 2 to 1, because I can lift 2 pounds with a 1-pound pull. But as always, there's a trade-off. In order to lift the weight a given distance, I need to pull twice that length of rope through the pulley. And by the way, this particular pulley arrangement is almost always inconvenient because I have to pull upward to lift the load. But if I reroute the lifting rope through an additional stationary pulley, like this, I get no additional mechanical advantage from that additional pulley, but now I can lift upward by pulling downward, a considerably more convenient arrangement. And this is precisely the arrangement of pulleys you'll find mounted on either side of my garage door, and probably yours too if you have a garage. The typical garage door weighs between 200 and 300 pounds, so I can't lift it without some help. And this mechanism provides the help. Note that it includes a moving pulley with 2 to 1 mechanical advantage and a fixed pulley, which only changes the direction of this lifting cable from horizontal to vertical. The cable extends from this bracket through both pulleys and then down to the bottom of the garage door where the other end is attached. The moving pulley is attached to a heavy steel spring. The key mechanical characteristic of any spring is that it stretches in direct proportion to the force it's carrying. More tension results in greater extension. In the lifting mechanism, the spring is stretched to its greatest extent when the garage door is closed. In this state, the large force in the spring is carrying most of the door's weight, and so I can lift the door with just a small additional upward force. As I raise the door, the stretch of the spring decreases, thus reducing the amount of assistance I receive from the lifting mechanism. But that's okay, because the weight I need to lift also decreases as the upper segments of the door rotate from vertical to horizontal. Now, the most perplexing characteristic of this system is that the pulley appears to be installed backwards. Note that 2 legs of the lifting cable counterbalance the spring force, which means that the force in the lifting cable is half of the spring force. In effect, this system actually has a 1 to 2 mechanical disadvantage. Can you guess why? Remember that all simple machines trade force for distance. This is actually a case where distance is more important than force. Because the garage door moves to a distance of about 7 feet as it's raised, a spring with no pulley attached would have to stretch more than 7 feet to provide enough force to lift the door through its full range of motion. This would require an impractically long spring. Instead, the system combines a more powerful spring with the backwards pulley configuration, so the spring only needs to stretch 3.5 feet, a far more practical arrangement. Of course, I could just install an automatic garage door opener, in which case the heavy lifting would be done by an electric motor. Indeed, the electric motor might be considered the simple machine of the modern era. Just think about all the everyday devices that are driven by this device. Fans, pumps, power tools, refrigerators, dishwashers, washing machines, dryers, air conditioners, microwave ovens, hair dryers, garbage disposals, disk drives, blenders, numerous devices in your car, and if you're driving an electric car or a hybrid, even the car itself. Now, there are many different types of electric motors. This model illustrates the inner workings of the simplest, a brushed direct current motor. Like a generator or a turbine, a motor consists of two major components called the rotor and stator. The stator consists of two permanent magnets, one with its north pole facing inward and the other with its south pole facing inward. The rotor here consisting of an electric coil that can rotate freely on an axle. Now, as you know, whenever current flows through a coil, it generates a magnetic field. And it's the repulsion between this magnetic field and the one produced by the stator that causes the rotor to start spinning. But it would only rotate through 1/2 turn and stop if it weren't for this component called the commutator, which reverses the direction of current flow through the coil with every 1/2 turn. Reversal of the current also causes reversal of the coil's magnetic field, causing magnetic repulsion to keep the rotor turning. Direct current is supplied through these metal brushes, which provide electrical connectivity while still allowing the commutator to rotate freely. Now, there are many variations on this theme. Some use electromagnets instead of permanent magnets in the stator. Some use AC instead of DC. Some use permanent magnets on the rotor so the brushes can be eliminated entirely. But regardless of configuration, the common feature of all electric motors is that repulsion between cyclically controlled magnetic fields is translated into mechanical shaft power. The electric motor has taken everyday technologies to a level far beyond anything that could be achieved with the classical simple machines alone. But just because this high-tech multifunction blender works doesn't necessarily mean that I can figure out how to work it. Next lecture, we'll consider this very different dimension of everyday engineering, designed for usability or ergonomics.